I'm CJ, and welcome to my workshop. This is a place where we like to have fun, talk about technology, and just try to find an overall nice balance in life between both playing with tech and getting outside and doing fun things. Heck yeah! Thanks for joining me today. We're going to take a look at generational improvements in NVIDIA GPUs. So looking at how architecture over the years has led to performance increases for AI workloads. And we're going to be comparing all the way from the Pascal generation back in 2016 all the way up to the Hopper generation today. Across the spectrum of GPUs, we'll kind of look at consumer GPUs, workstation GPUs, and server GPUs separately, as well as, some interesting details along the way. I think something interesting about comparing the generational improvements is, Huang's law, which is that GPU performance should double every generation. And I think we should take a look and see if that's accurate or not. And beyond that, I think it's also really interesting to see, even if it doesn't double every generation, are we seeing at least good efficiency gains? Because at the end of the day, I think we all want AI workloads to be as efficient as possible, as well as do the tasks that we want. And clearly GPUs have enabled this over the last 5 years especially. So that's kind of what we're going to take a look at today. And we're going to use the same benchmark suite that we kind of have been this whole time. And also all of the data will be available to you at a URL down in the description. Please take a look at the data for yourself, make some of your own conclusions, point out any data that looks wrong or might be wrong. If you have your own data, that would be great to share. And I'll keep sharing more about this benchmark in the future. It's going to be a public tool where anyone can submit data. We're just getting to the point where we can start doing that soon. So if you keep following along, that'll be in the future for sure. And I think with that, let's just start getting into the data, huh? So let's first take a look at our consumer grade GPUs. And here we're looking at the last 4 generation of GPUs, where the P102 is going to be our stand-in for a 1080 Ti, which I couldn't get my hands on for this testing. Here we're looking at Llama 3 8 billion. All of this is run with Llama files 0.8.8, and the model is at the quantization level of Q5KM. So that is our baseline, and we are only going to look at Llama 3 8 billion for our large language models today, mainly because the amount of VRAM generation over generation has changed. So we can't really have accurate comparisons with larger models. We'll look at this and just know that it's a constrained test, and that's what we have today. And we'll look at our workstation GPUs, which have much more similar VRAM for the larger models as well here in a moment. Just looking at the generation tokens per second, we can see massive improvements generation over generation for this particular workload. And similarly for our prompt tokens per second, how fast we can process the prompt here. And what this overall leads us to is our time to first token gets much better generation over generation, where the 4090 here is, like 5 times faster than the P102. Actually, let's take a look at percentages itself. So if we use our 4090 as our baseline, it is 500% faster than our P102. And we can see generation over generation, there's 71% slower time to first token on the 3090. And we can do the same thing for generation tokens per second, something like this, where let's use the P102 as the baseline here. And we can see just massive improvements. Though what we can also note is that this is not necessarily the same massive improvements toted by Huang's law. 32% generation over generation is nothing like a 2x gain, at least for this workload. And this is a relatively small workload. If we look at the 3090, we see another 13% gain year over year. Next, let's take a look at our diffusion benchmark. So this is using stable diffusion base at 1024 pixels. And you can clearly see just massive improvements. We can also see almost a doubling in terms of performance generation over generation, how long it takes you to get that image. And If we look at that in raw percentages as well, with the 4090 as the baseline, we can clearly see that massive jump generation over generation. And something here too is it's probably worth taking a look at our average iteration per second per watt. It's really interesting, actually, is that the 2080 Ti for this particular workload actually ends up beating the 3090, whereas even though the 3090 actually outperforms it in terms of raw generation speed, the 2080 Ti is more efficient in this particular workload. And the 4090 just absolutely crushes compared to all of them. And actually, let's take a look back at language for just a moment here in terms of our generation tokens per second per watt. And we can also see that same thing. The 3090 and the 2080 actually are quite similar in terms of their efficiency, and the 4090 is a big jump in terms of efficiency. Let's look at hearing briefly, and we kind of see similar kind of thing here. I don't think there's too much to say. These are the numbers. And finally, we'll look at Moondream, and this is for embedding images as well as captioning them. I think this is a very similar chart that we saw to Llama 3, 8 billion. Worthwhile looking at this data yourself. All of this will be available on the website linked in the description below. Feel free to take a look at all of this data and make your own conclusions. So now we're taking a look at our workstation grade GPUs, and these have had higher VRAM over their lifespan. We can use them here and get a better comparison of these mid-size large language models in that 27 billion size. Here we're looking at Gemma 2, and we can see the tokens per second generation over generation is better. But again, it is nothing like that Huang's law doubling, anything like that. So this is a good baseline to look at here, where we have the Quadro RTX 6000. We see a 17% improvement, and then another little bit of improvement next, and the A6000 to Ada, 25% improvement. That is nothing like a doubling in performance, but it is good nonetheless. And the efficiency, I think, is probably worthwhile to take a look at. And we can see the efficiency, again, that Ada generation is much, much more efficient. And we have our big daddies, the enterprise grade GPUs, the ones you spend millions and millions of dollars on. Here we can clearly see some performance improvements. Again, this is not going to be the most fair comparison because 8 billion parameters is not a great comparison for these GPUs, specifically with the amount of VRAM they have. And unfortunately, the P100 and V100 only have 16 gigs of VRAM, and the H100 and A100 have much more. So it'll be much more curious to see once Blackwell comes out. We'll probably do another one of these and compare the performance increase generation over generation from the A100 to the B200. This is what we're taking a look at here. It overall matches very well with the kind of consumer grade and enterprise or workstation grade that we already took a look at. I don't know if there's much more to say. Between the H100 and A100, the performance increase in this particular workload is not much. So I would say this is also very workload dependent, because we do see improvements, but how much improvement is a question. I guess one question is how much is it going to continue to improve generation over generation. Mainly just for fun is the performance of all of these GPUs just compared against each other, the workstation versus the consumer versus the server enterprise grade. And it's funny because you look at generationally, and the H100 compared to the 4090, they're basically performing exactly the same. And that's pretty remarkable to me. If we use the 4090 as the baseline, we see the H100 is 5% faster in terms of tokens per second generation. But when we look at something like our generation tokens per second per watt, the story changes remarkably, because the consumer grade GPUs, their default tuning is to have much higher power limits for gaming. However, that doesn't necessarily matter in a server context. You actually maybe want to optimize for efficiency and power density and compute density. So we do see, while it's only 5% faster, it is 30% more efficient. So that is where a lot of it goes. However, I think it'll be interesting to know when we get the data of, how does a 4090 power tuned compared to an H100? These GPUs, while they're consumer grade and you're not supposed to use them in the data center, certainly they provide a absolute ton of value in terms of inference performance. And I think at-home inference in a distributed capacity maybe actually makes a lot of sense. and is a lot more cost effective than a huge capex spend on H100s or A100s. The last thing I want to explore today is looking at our big generational improvements in terms of what happens when we look at skipping multiple generations. How is that? And so here we have the Tesla P40 versus the NVIDIA L4. Why I picked these two to compare is that the L4 is a 72 watt GPU and the P40 is a 250 watt GPU. So because of this, I think it's just interesting to look at just some of these raw graphs. We have the L4, which is the Ada Lovelace generation, outperforming the P40 at 72 watts. If we actually just look at how much power it's actually consuming, you can see the P40 is at almost 200 watts, whereas the L4 is at 70 watts for that same exact workload. This is pretty amazing, I think, just to see how much less power you're consuming. Very impressive. And I think we can take a look at bigger models as well. So we look at Gemma 2, for example, and we'll take a look at our generation tokens per second again. This time the L4 is a little bit behind, but in terms of its performance per watt, just absolutely destroys the P40. Same thing in generation, that was prompt. This is almost a 3x increase in terms of performance per watt, and that efficiency, I think, really matters. That's just something I really wanted to highlight here, is that maybe the biggest thing you get generation over generation is not the raw performance itself, but rather the efficiency gain. That's even more obvious when you look at something like Stable Diffusion, where we get 10x the performance in diffusion for 4x less power, something like that. Let's look at the average iterations per second per watt. Look at just this massive difference. That's 16 times better performance per watt. That is remarkable. In conclusion, I think what we saw today is that Huang's law is not broadly applicable generation over generation. We don't always see a 2x improvement generation over generation. For some workloads and even parts of some workloads, we do see that. Something like prompt processing for large language models, we did see that big improvement. And similar for Stable Diffusion, we saw these huge generational improvements. However, that wasn't the case for everything. Like token generation speed didn't necessarily go any faster. So that was pretty interesting to me, and I think it'll be curious to see with Blackwell and everything in the future what will happen with this as well, and we'll continue to test that. And the other thing to me that I found fascinating was the efficiency gains generation over generation. The original architecture that we tested today, or the first architecture we tested today, was Pascal, and that was released back in 2016. And we compared the efficiency versus Ada Lovelace, which is 2022. And in that 6-year period, we saw almost a 4x gain in efficiency, which is pretty dramatic. I think that is really nice. To do the same workload at 4 times less the power is very important, and I hope we continue to see those kind of efficiency gains as AI becomes more ubiquitous in the world. I think it's really important that that's the case. And it also means that it becomes more accessible to every individual. If you don't need to be running 300 watts of power, but you can run something at 5 watts in your pocket. That's a pretty remarkable change, I think. And I think we'll continue to get there, and it'll be very curious to see how fast we get there. So with all this said, I think there's some upcoming things that I'm pretty excited about, and pulling on some of these threads as well. So first is, well, when I can get hold of Blackwell, that certainly will be something else that we're going to test and compare, because we'll then at least have the A100, H100, and B200 to test against. And we'll be able to test much large language models. Maybe we can test a variety of quantizations, see if Huang's law is applying, at least on the inference side. I'm not going to be testing training for now. However, maybe in the future I will also test training. But for now, that's the case there. And I also have a bunch of upcoming topics that I'm curious about as well. A lot of them are playing with, say, AMD GPUs, and maybe even some tutorials on how to get AMD GPUs working and accelerated on Linux. Similar for Macs, I want to test a bunch of Macs and see, well, how does the performance scale with the number of GPU cores you have? Because, of course, these M1 or ARM-based Macs have pretty incredible performance per watt, and it would be really interesting to see how that compares against NVIDIA GPUs as well, especially as Apple is starting to go towards this on-device kind of inference. I think that's a really interesting topic of exploration. Of course, I think there's some single board computer stuff with AI that I want to play with and show you in the future. That'll be fun. And yeah, of course, when everything continues to develop, I'm really excited to share the benchmark with more people, get it working so anyone can submit their own data, and that'll be great. So anyway, thank you so much for joining me today. I hope you learned something, and I hope you have a wonderful rest of your day.